most of chapter 1, I think, is review material for you. It's pre-calculus stuff. I'm not going to go over every little thing, but I'll go over some of the interesting, some of the important and interesting points. So section 1.2 is the plane. So we have the real numbers, right? The real numbers, and we think of these as corresponding to a line, right? In one dimension, we think of this thing as the number line, because zero is in place, and then there's positives. Right? So this is you think of this as a one-dimensional thing, and each point on the line you think of as corresponding to some real number, right? The number line. Like I said last time, to the Greeks, or maybe in the first class, to the Greeks, numbers were lengths, and what really bothered them was at the time, what number, what ratio was this length here? What was this length here? It bobbled them. They considered it to be beyond description, like I think they used like beyond words, or beyond language. Okay, so in two dimensions, right? In two dimensions, we have this line, right? So we have this line. We have numbers associated with it. Initially they were rational numbers, and then later on it turned out that there were some things that weren't rational. There were a lot, in fact, a lot of holes in there were a lot of lengths that could not be described as rational numbers. Okay. Now, so we have then the real numbers, and then we have the plane, right? So plane, two dimensions going in all flat and going in all directions, right? And so it's a flat thing, and so what we normally do, right? What do you do in two dimensions? Normally, so the common option is to take two number lines, right? As you know, you take two number lines and you say to each point, just as to each point on the line there corresponds a number, to each point in the plane you let correspond a pair of numbers, right? X and Y, right? Where X is, you get X by, so here is one number line and here's another number line. You drop down to, you drop a parallel, and you drop a perpendicular down to here, and you call that thing X, and you drop a perpendicular over to here, and you call that thing Y. And then you associate each point to this point with a pair of numbers X, Y. Right? And because of that, we call the plane R2. Right? R2. Right? R2 denotes, we used to denote the plane. This is so-called Cartesian coordinates. And the story is that Descartes was watching a bug in his room while he was trying to go to sleep, and realized that the position of the bug, the position of the fly, could be determined by its distance to one wall and its distance to the other wall. Right? And this allowed him to start thinking about analytic geometry, which was actually a huge breakthrough. Okay, so that's one option. Putting coordinates on the plane. Does anybody know another possibility for putting coordinates on the plane? What's another possibility for putting coordinates on the plane? Here is one. Right? To each point, you associate these two numbers, you get them by dropping perpendiculars. Another one.
I can't remember what it's called, the circle one?
Yeah, the circle one. I think the circle one, which is called polar coordinates. Okay. Polar coordinates, right? So you have a circle with center, right? And you have a ray emanating from the center, right? And to each point, you associate a pair of numbers, but that pair of numbers you don't get in the same way as before, but rather you go down, you look at the, let's say like this. So you get the angle in a positive way going going from the ray. So you measure from the ray up in this direction, and you call it in radians, and you call the thing theta. And you make a big circle and drop down here and see this. Call this thing r. Right? This r is of course the distance to the point. Right? So maybe I didn't need to drop all the way down to this line. I could have just said r is this distance. So r is this distance, and then theta is this. And then every point in the plane, to every point in the plane, you associate this pair of numbers, r from theta. Right? And in that sense, you would call, we could call the plane the positive real numbers cross the circle. Okay. And for some reason, we spell circle with an S. Right? But that's fine. We don't spell it with a C. Okay. Right, so this R2, you think of it as R cross R. Right? R cross R. You've got the real numbers cross the real numbers. Over there, you've got the positive reals cross the circle. Okay, so that's those are two things. The second one is not so important for now. It will show up later. Okay. So other things that you've probably seen before: notion of distance, right? In one dimension, so back to one dimension. In one dimension, one has a notion of distance. Describe it, right? The distance between 2 points is the absolute value of the difference between them. You've got x and y, that are just numbers, so the distance between them is the absolute value of the difference. Okay. And right. What about in 2 dimensions? What do you have in 2 dimensions? Does anyone remember? You've got 2 points, right? Suppose you've got x1, y1, x1, y1, x2, y2, right? Then you have a way of describing the distance, right? The distance between these guys is something that you've probably seen before.
Oh, I was going to say the y2 minus y1 over x2 minus x1.
I think you're mixing this up with something else.
X2 minus y2, or y2 minus x2. I don't know. I'm just thinking.
That's it. You don't.
Square root of x2 minus x1, the quantity squared, plus y2 minus y1 quantity squared.
Right. So y2 minus y1 quantity. So yeah, don't. I'm glad. Please feel comfortable to just say whatever, and don't. Let me say right now that when I was learning Chinese in college, the Chinese professor gave us good advice, and he said, "The key to learning is shamelessness." That is, when you're a kid, right? You just speak, and then you get correction. You can speak. You don't really care how you speak, right? You speak and you get correction, and then you learn very quickly. And when you're older, like I probably said only 2 or 3 things throughout my entire college career. This is not that great an exaggeration. Oh, certainly fewer than 10 things I said in class. Throughout my whole college career. Right, my heart would start pounding, and I'd be like, this question. Heart start pounding. Maybe wouldn't raise that. So yeah. Anyway, so I know, just ask questions and get corrected, and that's the quickest way to learn. Yeah, and I carried that out pretty successfully in Chinese class, at least. Yes?
Are you going to review the point slope formula also?
Yes, we will. Yes, we will. So that will come next. So, yeah. So, those of you who've been in my class before probably mention or even tell this story, but once I went to Taiwan, my family's from Taiwan, and I went to Taiwan, and using my brand new Chinese, started. Well, it wasn't that brand new. It was maybe 10 years after I started learning Chinese. I started speaking to the immigration people in Chinese, and they said, "Oh, where are you going?" I said, "Oh, I'm going home to Banqiao in Taiwan." They said, "Home, huh? Your accent doesn't sound like you're from Taiwan," because I sounded like I was from mainland China, and having so shamelessly, having gotten so much correction in college that I sounded very much like I was from mainland China. And so eventually they said, "Why don't you go with these 3 people over to the side for some questioning?" And because Taiwan and China are not exactly friendly. But anyway, it's kind of a long story. But I was released after an hour. After that, I wrote back to thank my Chinese teachers for having done such a great, amazing job. Okay. So yeah, the distance formula, right? The distance between 2 points. You take, the difference of the x's squared plus the difference of the y squared, and you take the square root, right? So if, for example, I said, what's the distance between these 2 points? Right? What's the distance between these 2 points? Take 10 seconds and work it out. Or just think about it. So what's the answer? Don't put it out, please. Somebody raise your hand. Leanna?
2?
The distance is 2? Is it 2? Let's see.
Yeah.
So
Never mind. That's wrong.
let's see. The square root. Let's see. What do we do? We're
Oh,
going to take
I
the
used
difference
the wrong
of the x's.
formula.
We're going to take the difference of the x's. Right. So 4 minus 2 quantity squared, and then we're going to take the difference of the y's. 5 minus 1 quantity squared. So you get the square root of 4 plus 16. Right. So the square root of 20. All right.
Yeah.
So the square root of 20. Right. Everyone familiar? Okay. So where does this come from? Where does this formula come from? Why is this the right formula? Why is this the right formula? Ellen.
It's from the Pythagorean theorem.
From the Pythagorean theorem, exactly. Right? So you think about it, you say, okay, if I have 2 points, here's say x1, y1, and here is x2, y2, right? And I want to know the distance between the 2 points. Well, I want to know the length of this line segment here, right? I want to know the length of the line segment. Well, I can figure out the length of the line segment by drawing a right triangle here, right? And what's this length? This length here is the difference. Well, it's this is x1 and this is x2, right? So the difference is the bigger minus the smaller. Or maybe it's better to use the absolute value. So I'm going to say the absolute value is x1 minus x2, right? The distance. What's the distance? We just said. In 1 dimension, the distance between 2 points is the absolute value of the difference. Right? Absolute value of difference, absolute value of the difference, right? That's this length. Yeah. Right? And so what's this? Sophie?
The sum squared.
Mm-hmm.
The sums of both sides, a squared plus b squared.
Yeah, so if I square this, then I'll get the sum of the squares.
Yeah.
So I want to take the square. So this length, d, I'll call it, e is going to be square root of a squared plus b squared. And maybe we can make it consistent with y1. Okay, which is the same thing as what we wrote up here, right? Because the square of an absolute value is the same thing as the square of the number. If you like, animate it this way, so let's do it. Okay, so that's why this makes sense. And you can sort of guess what happens in more dimensions. What happens if we're in R3, say? Another?
So it would be the square root of x1 minus x2 squared plus y1 minus y2 squared plus z1 minus z2 squared.
Yeah, and so on and so forth. Right? In n dimensions, you just take the sum of the coordinates, the sum of the squares of the coordinates of the n coordinates, quantity square rooted. In the end, you know there's going to be a square root because there's a Pythagorean theorem. Okay. And you see that if you reverse the points, it doesn't matter, right? Because x1 minus x2 squared, you know, the distance between x1 and x2 is the same thing as the distance between x2 and x1. And
When you're doing like with Z or any n dimension, what distance is that? Is it on the line then? Is it? What did you do this, right?
So if you're in R3, say, it's still the same thing. You have 2 points in space.
Right.
So you're measuring the distance between these two points in space. Right? Okay. Other questions? Okay. So going onwards or going backwards, the circle. Right. What's the equation? Somebody tell me what's the equation for a circle. Suppose you have a circle with center at some point on the plane and some radius r. What's the equation for that circle?
So, as I remember it, it is x squared plus y squared is equal to r squared.
X squared plus y squared is equal to y squared. Okay.
And then
So but you see this, you can see that there's got to be some problem there because where are the x naught and y naught? Right? There's something else that has to factor into this. Mike?
I would just do x minus x naught, so that's the center, and then y minus
X minus x naught?
squared. Minus, or I think it's plus, y minus y naught squared equals r.
That was awesome. Anybody else? Part of being a professor is the ability to keep a really blank face. Yes. Fortunately, I was born with a blank face. So yeah, actually this is it, and this makes sense. Like, if you look at this thing, if we take the square root of both sides, what is the same? Let's write it like this, okay? Instead of writing it like this, I'm going to write it like this, which is the same thing. Okay. I'm going to write it like this. And then you think, okay, what is this? What is the same? What is the same? I'm going to look at the points x comma y that satisfy this formula, right? And that should be a circle. Why should that be a circle? Why should that be a circle? So think about it without, you can talk to each other, but just think about it for like a minute or so.
Yeah.
Yeah, but it's obviously like why?
Where the center is going to lie. So that X not Y not splits to there and then each factor is I mean, you caught that, but yeah, you could. But yeah, but it's like more specific because that it doesn't change.
So why?
Because that's a form of the distance
Yes.
formula, so you're finding points that are equidistant from the center point.
Exactly. So what this says in English is I'm looking at all xy whose distance, right, this is the distance of xy to x naught y naught. Right? The thing on the left is the distance to x naught y naught. So I'm looking at all points xy whose distance to x naught y naught is r. Right? In other words, I'm looking at all points any point whose distance is r. Right? All points that are equidistant from some center. In other words, a circle. So if you ever forget the formula for a circle, just reconstruct it from the distance formula. Okay? And if you forget the distance formula, just reconstruct it from the diagram here. And I hope you don't forget the diagram. Just don't forget the diagram. Okay. Questions? Okay. So sort of standard exercises. Like find the center of radius. Some circle. So somebody gives you a circle, and it's in a form that's slightly disguised. 2x squared plus 2y squared plus 8x minus 4y plus 6 is 0.
Is that
2x squared plus 2y squared plus 8x minus 4y plus 6.
Does that, I'm sorry, does that say find center and radius or of radius?
So find the center and radius. I tend to use this thing with and.
Okay, sorry, I didn't see it well.
Okay, so what do you do in this case? Or should I let you try it? Try it. Take half a minute and see if you can do it. Just as a refresher. Maybe 1 minute. Okay, turn to somebody next to you and say what you got.
negative, I say I put the negative. So, and then what I did was basically a factor, you get 2x times x plus 4, 2y times 1, 2 is equal to complement of
Like the radius is r squared, so you have to choose
Okay, okay, so who would like to say how you did, kind of?
So the first thing I did was divide by 2.
Divide by 2?
Okay.
Great. Multiply the whole thing. Multiplying the whole thing through by a non-zero number, doesn't change the solution set.
And then, so I separated x and y.
Okay, so put these guys together, put these guys together.
And then I completed the square.
Complete the square. You said x plus 2, quantity squared plus 4, minus 1, quantity squared plus 1.
And then all the constants I just put on the other side.
Mm-hmm. X plus 2 squared plus y plus minus 1 squared equals 2.
So you have your center -2, 1,
Mm-hmm.
your radius.
Negative 2, 1, the radius, root 2. Okay, yeah, that one.
Would it have still worked if you had it divided by 2 in the beginning?
It would have worked. It would have been sort of, everything just would have been multiplied by 2. It would have been harder to do.
Okay.
It's easier, at least it's easier for me to do completing the square if the coefficient of the square term is 1. Any questions? Right, so here we just divided by 2, so divide 2. Okay. Okay, as long as we don't multiply by 0 on both sides, that's okay. This is just grouping, nothing happened. So dividing by 2 doesn't change the solution set. And here we just rewrote it using completing the square. Right. So you recognize this x squared, right? This x squared plus 4x. You recognize that it's going to be x plus 2 quantity squared, right? But you have to get rid of the constant term that you added on. Right? This x plus 2 squared, right? X plus 2 squared is equal to x squared plus 4x plus 4. Right? And so you have this thing and you're thinking, I'd like to make this into a square. Well, the square that's hopeful, the square that's most likely is this, the square that's going to work is this guy, x plus 2 quantity squared. Right? But it's not, this isn't x plus 2 quantity squared. We have to subtract out the constant term to make it equal. Right? So you get, right, so this thing turns into this thing turns into this. Right? And now we've got it in squared form, and then we make it look like a circle. Any questions? Suki? Anybody? Okay. Another example of the same, using the same, another example, using the same technique. Okay. So here is a parabola. Somebody says graph the parabola. Y equals 2x squared plus 5x plus 1. Parabola 2x squared plus 5x plus 1. Okay. So there are a couple ways you could do this. maybe the way that that I'll suggest, here's one way, okay, and it's involving completing the square. So I'm just going to write this as 2x squared plus 5/2 x plus a half. And I'm doing this sort of to illustrate using completing the square, but and then I'm going to be completing the square here. So take 15 seconds and complete the square inside. And tell me what this x squared plus 5/2 x will be equal to if I write it as a square minus some constant. Would somebody like to tell me? Or, yeah, Alfred.
So this is just for completing the square?
Yeah,
Okay.
just tell me what I need.
So 2 parentheses x plus 5/4 close parentheses squared minus 17 over 16.
17 over 16. Well, let me slow it down and put the minus 25 over 16 plus 1/2. Okay, just to make it clear what's what. Okay. So so this thing is the things that are underlined are equal to each other. I hope everybody got that. Right? You've got your x squared plus 5/2 x, and you write it as right. You take this is going to be x plus 5/4 quantity squared, and then you subtract off the square of this thing, like 25 over 16. Right, whenever you have x squared plus ax, right, you write it as x plus a over 2 quantity squared minus a over 2. Okay, that's the general. Okay, so let's 2x plus 5/4 squared minus 17 over 16 is what y is equal to. So here's y, and depending on what x you give it, you're going to get a different y, right? And so the question at the beginning, you may recall, was to graph the parabola here. So let's think about this thing here. Let's think about our equation. Okay, let's think about this expression here. Okay, where is this thing? So the parabola says, give me an x. I'm going to add it to 5/4 squared, subtract 17/16, and then multiply by 2. Okay. Right, so where is it going to give you the smallest reply? For what x is this thing going to be the smallest? Don't put it up. Think about it. Yeah, actually, I'm going to go outside. So think about it. So think about it for a minute. And you can talk to each other. For what x is the y going to be the smallest?
Yeah, because even if it was negative, it would be squared, so it would have to be
Why would x squared plus 5 over 2? Like, why can write that again on the other side? I don't know why. Right, so you don't finish that, right? Oh. Okay, so they have Oh, okay, I see. Okay, so,
So normally I wish I smoked or did something so that I had something to do while I was outside. Now actually I do. I do martial arts, and over the summer I completely destroyed my body. And so I'm actually stretching out there, trying to reduce the pain. So it's good. I have something to do on that. So who has an answer? Who has an answer? Helen.
Well, we came up with negative 5/4.
Negative 5/4. Okay, so at x equals negative 5/4. Anybody else? Okay, and why do you think that?
Because we said that x is the only part that we have control over, so if you made that sum that you're going to square is 0 essentially, so negative 5/4 plus 5/4, then it would just be negative 17 over 16.
Yeah, that's right. Because you look at this thing, the construct says, whatever you give me, I'm going to add it to 5/4 and square it, right? So this, you're going to get this number, this number is going to be 0 or bigger, right? Because it's a square, right? The smallest this number could be is 0. When does that happen? When x is negative 5/4. Right? The smallest this number, because the smallest x plus 5/4 squared can be is 0, and that happens at x equals negative 5/4. Right? Okay. So you know that at x equals negative 5/4, this thing is at its minimum, right? Right. So at negative here is 1, saying at negative 5/4, you know this thing's at its minimum, negative 34 16ths. Right? And so this something like this. And so you know also that that's the axis of symmetry, right? That's the location of the axis of symmetry, etc., etc. Any questions? Sharon? Question?
Oh, no. I thought I heard you wrong. I thought I heard you say maximum, but it's minimum.
Minimum. Any other questions? Okay. Right, so I mean, you could well remember, so maybe sometimes if you just memorize things, you could say, oh, this is the form y equals a squared plus b equals c. I know the axis of symmetry is going to be a negative b with 2 ways. Right? The axis of symmetry, blah, blah, blah. So, but if you forget these things, and I never remember these things, but you can always figure them out. Just look at it and use simple tools. So, I think that the less you memorize, the more you understand. So everything that we've done can be reconstructed from the Pythagorean theorem, completing the square, very simple things. Okay. So onwards. something that we were starting to hit earlier, lines. So there's this geometric notion of a line, so geometric notion of a line. It's this thing that goes, it's straight, it goes on infinitely in both directions, right? Okay, and we'd like to describe lines algebraically. Right, once you have your coordinate system, right, once Descartes has put coordinates on the plane, we can talk about this as in terms of equations, right? So more algebraically. Okay. So okay. So the first thing we can do is find the notion of slope. So, notion of slope. You have these 2 points. Suppose you have these 2 points, x1, y1, x2, y2, on the line. And we define this thing, the slope, like we call the slope the ratio of y2 minus y1 or x2 minus x1. And so that's what Suki you were remembering earlier. Right? It is the ratio of this difference to this difference, right? So, right, y2 minus y1 is this, but it has a sign on it, right? It's not a length, it's a signed length. It could be positive, it could be negative, right? x2 minus x1 is this, right? Again, a signed length. Right, and the slope is the ratio of these signed lengths. So, right, so that thing is called the slope. One usually denotes it by m, with an m. I'm not sure why. So it's the so it's the sign ratio, sign ratio of the lengths of the triangle. So let me ask a question. Does it matter if we change the order? Does it matter if we change the order? Does it matter if we change the order? Suppose we take y1 minus y2 over x1 minus x2. Cynthia?
No.
No, it doesn't. No, it doesn't, right? Because we're going to get, we'll just get the same thing. You'll get minus on the top and minus on the bottom. Does it matter if we change if we take 2 different points? Right? Suppose we take, instead of those 2 guys, so here are our first 2 guys, suppose we take instead these 2 guys. Right? So, right? Does it matter? No, why not? Why is the ratio the same?
Because same line.
It's not the line.
Similar triangles is right. And you've got a triangle here, right? You've got a triangle here. These guys, right? These are the same angle. These are the same angle. And so the ratio of this length to this length is the same thing as the ratio of this length to this length. So by similar triangles, the ratios are going to be the same. No, because of similar triangles. So, so what does that tell us?
So it basically tells us that, you know, no matter what points you take, you will get the same slope throughout, because it's a line.
Yeah. Yes, that's true. Kylie?
A line has a constant slope.
Line has a constant slope? Yes. Sorry, I actually was, sorry, let me, it was actually a rhetorical question. That's why I should have, like, I'm sorry, maybe, is there some way to distinguish rhetorical questions from not? So sorry. So, anyways, what does that tell us? Rhetorical question. What does that tell us? What does that tell us? Maybe if I write it up, it's a rhetorical question. No, it's still not. Okay, so if we fix a point on the line, if we fix a point on the line, x naught, y naught, and we look at an arbitrary point. Okay? Let x, y be any point, any other point on the line. Then we know that then y minus y naught over x minus x naught is constant. Right? It's constant. As that x moves, for whatever x we choose, that's going to give us the same thing. Right? That's what you guys are saying. The slope doesn't change. The slope doesn't change. So this is a constant, right? Some constant m. Right? So the line is determined, right, is those points such that y minus y naught over x minus x naught is constant, right? In other words, such that y minus y naught is some constant times x minus x naught. Right? And that's why this is the formula for a line. Right? That's why this is the formula for a line. Okay, let's stop there. Good.